Okay, so what I'd like to do is continue on looking at the modeling of molecules in three-dimensional space. My internet is finally stable today. Yesterday it was on and off, on and off. My plants got knocked down. It was quite a day. Okay. What I'm going to do is look at a multi-central atom setup today. Now, last time we looked at only one central atom. Excuse me. I'm going to do one central atom today, and then I'm going to jump to multi-central atoms using this formula here and this formula here. This one has 3 central atoms. This one has 2 central atoms, and that'll be obvious after we do the Lewis dot structure. And quickly, there. Okay, all right, so let's look at this here. OCCl2. What is that going to look like as far as a dot structure? That's the first step, do the Lewis dot structure, okay? So carbon's going to be in the middle. I'm going to have two chlorides and then a double bonded oxygen. Now, we're only going to look at the central atoms now, not the peripheral atoms attaching to the central atom. That is very important, okay? That means you're only going to be looking at these guys here. Just like we did up here with the nitrogen, the fluorides, other than the bond, we're not looking at the electrons around the peripheral atoms, okay? So that's the dot structure, okay? So we have three electron domains. That's the one double bond and the 2 single bonds. Remember, the double bond and a triple bond count as one grouping of electrons or one electron domain. So that's going to be trigonal planar. All right. Now the number of bonding domains is going to be 3. The number of lone pairs that are not bonding is 0. That means this is going to be trigonal planar and with a bond angle of 120. Now, whenever this is 0 here, the electronic and the molecular geometry is the same. Okay, so whenever this is 0, in other words, there are no lone pairs or no non-bonding pairs, then the electronic geometry and the molecular geometry are going to be the same, which is the case here. All right, so let's now try a multi-central atom. Okay, so the first thing we're going to do is draw the dot structure. Okay, that's going to look like this. This bigger. Okay, now how many central atoms are there? Well, there are 3, because remember, a central atom has 2 or more atoms attached. Okay, so that makes the carbon which has 4 atoms attached, a candidate, the oxygen, which has 2 candidates attached, and this carbon over here has 4. So that's a candidate also. So there are 3 central atoms here. That means we're going to have to do this 3 times, 1 per central atom. So one way to do this is just have 3 separate analyses, 1 per central atom. Okay, so let's take the carbon one first, then the oxygen, and then the other carbon. And let's call that. Now the 2 carbons are exactly the same. Okay, so let's do the carbons first, okay? It has 4 sorry about that. I'm trying to. Okay, so it has 4 electron domains. That makes that tetrahedral. Four bonding and 0 electron pairs. And remember, that means that the electronic geometry and the molecular geometry are going to be the same. So that makes that tetrahedral. And that would be 109.5 degrees. And since the carbons are exactly the same, that means these are going to be the same. Okay, now what about the oxygen? Okay, the oxygen has 4 also. 1, 2, 3, 4. That means the oxygen is tetrahedral. But it has 2 bonding and 2 non-bonding. That means that is bent or angular. Okay, so that's falling into right down here. 2 and 2, and it's bent or angular. And the angle is going to be much smaller than 109.5 because these 2 non-bonding pairs of electrons push those 2 carbons closer together. Okay, and since we have no one live, I'm going to ask you if this makes sense. And of course, everyone's going to agree because no one's there. Excuse me. All right. Okay, so let's look at this molecule here. Okay, this happens to be acetic acid, which was one of the molecules we were looking at Lewis dot structures for. And remember, there were 8 structures. Now, any of those would work here. And what I'm going to use is going to have a different breakdown than if you use one of the alternate structures. On a test, any of the alternate structures, as long as they're legal, you can do an analysis of. So if I asked you to do an analysis on this formula and you chose one of the alternates and did the analysis correctly, then that would be fine. So long as you did it correctly based on the legal Lewis structure. Okay, and there are 2 of these. So I'm going to divide this up. And okay, so it's going to, let's make that bigger. Okay, so how many central atoms do we have here? Well, we have carbon has 4 bonds, 4 atoms attached, so that's a candidate. This carbon is a candidate, it has 3. This oxygen has 2. This oxygen has 1, so it's not a candidate. So we have 3 central atoms. So this is going to be the first carbon, second carbon, and then the oxygen. Okay, so let's take the carbon on the left. And that's going to have 4 electron domains. That means electron geometry is tetrahedral. The bonding domains are 4 and 0 lone pairs. Now this is the leftmost carbon. Okay, so that means the molecular geometry is going to be tetrahedral again, because that's 0. So the bond angle is 109.5 degrees. And let's take the second carbon. Second carbon has 3. That means this is going to be trigonal planar. Remember, there are 2 trigonals now. There's trigonal planar and trigonal pyramidal. One's 3-dimensional, one's flat. And this is going to be 3 and O. That means this is going to be trigonal planar, because this is 0, and the angle is 120. Let's look at the oxygen now. The oxygen has 4. That means that's going to be tetrahedral. Bonding pairs is 3. Oh, excuse me. It's 2 and 2 non-bonding pairs. So that would be bent or angular. You'll see bent more than angular. And that angle is going to be lots less than 109.5. Now, sometimes in classes, they'll tell you that's going to be 104, but it depends. So I just like to say it's significantly less than 109. Okay, so that's some examples of multi-central atoms, and I gave you lots of practice on that. And in modules, Canvas modules, I give you the answers to all of these. Now, again, it depends. There are alternate structures for all these as well. So if you choose a structure that's different than mine, your VSEPR analysis is going to be different than mine. Okay, so I'm going to end this now. I'm going to start on chapter 5. Now, chapter 10 is basically looking at ways of drawing from a formula. And the formula doesn't tell us a lot about the structure. And it doesn't tell us a lot about the chemistry because we're not looking at the structure. So once you have the structure, and this is the best way using the VSEPR analyses, you can tell a lot of the chemistry. And then from there, you can then do lab tests to determine if that analysis is correct or not.